Welcome, welcome, my lovely students. So today we are looking at, so up here it says 2A-1. We're going to do a number of days that are theoretically situated within section 2A. If you actually read section 2A in the book, the part they talk about fractions is this big. And we're going to expand that into multiple days, which is not a bad thing. Fractions are an interesting thing to talk about. Okay. So when a whole unit, whatever size or shape that is divided into equal parts. Now, the equal here is the critical important piece here. We don't talk about fractions unless all the parts are the same size. So we call those parts fractions of a whole. However many pieces it's divided into, if it's 2 pieces, then we would call one piece a half or 1 out of 2. If it's 4 pieces, we would call a single piece 1/4 or 1/7 or 1/16. However many pieces there are, as long as they're equal or as long as we assume they're equal, because drawing perfectly equal parts is kind of a pain, we call those fractions. So a unit fraction, let's use an actual pen. Is a singular piece. So like 1/b. So it could be like a half, a fourth, just as long as the top is 1. This represents one piece of the size we're talking about in relation to whatever we define as the whole. A lot of times I think of either a big pizza or a big pan of brownies, depending on what kind of fraction they want me to cut it in, because I don't want to cut a pizza into 17ths. I don't really want to cut a brownie into 17ths either, but I could figure it out better with the rectangle. Now, once we start having more than one of those fractions, more than one of those unit fractions, that's where we get this A over B. So A is the number of copies of the unit fraction 1 over B. We've just merged it into a shorthand of A over B due to the properties of math. So hopefully this is vaguely familiar with the terms we use. The top is called the numerator. The bottom is called the denominator. So the denominator tells us the number of equal pieces into which whatever a whole unit is divided. So the size of the pieces. The top tells us the number of copies. So the numerator is the number of times the fraction is enumerated or copied. The denominator tells us the denomination of the size of the fractions. So the words are actually chosen deliberately. A fancier name for fractions is rational numbers because these are all ratios, one thing over another. All right. So now we're just going to label numerator and denominator. We'll do it with fancy colors. So we're going to make numerator yellow, and then we'll make denominator squiggly green. So 5/12. So this is, if I take a circle and cut it into 12 equal pieces, 5 of them would represent this fraction, which would be a little bit less than half the pizza. So 5 is the number of times that the piece of size 1/12 is enumerated. Now it turns out it doesn't matter what we write in the top and the bottom, like up here, A and B. A is the numerator, B is the denominator, because I put a little bar in between them and called it a fraction. So same thing over here. This ridiculous 67m is the denominator, and the 24x on top is the numerator. So when they throw in letters in there, letters are just a placeholder for, I don't know what this number is, but I might figure it out. I might not. And for problems like this, it's there to sticker shock you. So when you see a problem that your immediate gut reaction is like, ugh, I want you to remember, we are not your previous math teachers. We are not constrained the way your high school teachers were. They had to prepare you for a test they didn't get to write. We get to write all your tests. So trust us to write fair assessments. For me, if there's a question that you didn't understand, you ask me right then. Or when it's graded and you don't understand why I graded something the way, ask me. I'm not infallible. I can make mistakes, especially if my daughter's running around behind me and screaming at me. So trust us to write fair assessments that you can do in the time provided, and we'll trust you guys to work your hardest at it. Not an impossible amount, just give it your best effort, whatever that happens to be for each of you. All right, so now we have pictorial representations of fractions. Yay, pictures. So we have to write a fraction that represents the colored or shaded area. So in order to do that, we first have to know what size are these pieces. Now, what the directions should but don't say is assume each of the pieces is the same size. In the drawing, they look about that, so we just kind of assume you'll assume that, which kind of bothers me. It really should say it. But here, let's just grab a pen. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 equal pieces, so we know this is eighths. Then we want to count the numbers that are shaded. And there are 5 of them. Now, for some of y'all, this might feel a little like, why are we doing this? I taught a elementary math methods course last semester, which is the course that future teachers will take. And I assume you guys at some point might interact with children. So it doesn't hurt to have this kind of base level knowledge. Plus, honestly, my teachers never taught it this way. And after teaching that class, I really wish they had. It would have helped. I got some thoughts on division too, which we're going to get to. All right, so same idea on B. I need to know the size of the parts. And you don't have to write the numbers. I mean, a lot of times I just kind of put dots as I count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So they each have 1 dot and only 1 dot. So I've counted them all exactly once. So there are 9. And then we got to count 1, 2, 3, 4. 4 of them are colored in. So the shaded colored part represents 4/9. Now C is a little more interesting, and there's actually fraction tiles elementary age kids get to use, and they're shapes that can be made up of these triangles. So they'll have triangles and diamonds and half of the hexagon, which is a trapezoid, and then the whole hexagon. And they're all set up so like 2 trapezoids would cover the hexagon. So I could then say that the trapezoid is half the size of the hexagon. It's a really good way of getting kids to relate to how to represent fractions. And the equality between fractions, like you can see some are thirds and some are sixths, and how 2 sixths fit into 1/3. It's really nice. So in this one here, as we can see, our hexagon has 6 triangles in there. 1, 2, 3, 4, 5, 6 pieces. And then we count how many are shaded in. 1, 2, 3, 4, 5, 6. There we go, 6 sixths. A slightly silly answer, but still, that is what they gave us to represent. Now, D can look a little weird on first inspection because the first 3 were regular polygons. D is not. D is a weird trapezoid that's been cut up into equal triangles. But if you look at the triangles, like if you flip them around, they are supposed to be the same size. So we're going to make that assumption. Otherwise, we can't answer the fraction question. So let's count how many we got. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 funky shaped triangles here. So those triangles, assuming the whole shape is a whole, then those are 9ths. And we check 1, 2, 3, 4, 5 of them are shaded. So that picture represents 5/9 of that funky shape. All right. Now, same kind of thing in 2, but we're going to do it with words. So a box contains 7 orange balls, 8 green balls, and 4 red balls. What fraction of the box is made up of red balls? None, because the box is not made up of balls, it contains balls. This is one of the problems with math. Sometimes the English person gets a hold of the question at the end. Contains sounds funky and weird from an English writer perspective, but the mathematician says, but that's what is happening. If you say made up of, you're saying the box is made up of balls, and it's not made up of balls. That is silly. So sometimes when you read a question and you're like, it sounds kind of clunky and weird, that means the mathematician got the final say on it, which means it translates more directly. You don't have to apply this kind of common sense thinking to it. And I know you guys have good common sense. It's just the mathematician in me is like, mm-mm. So we know or can assume that they mean what fraction of the total balls are the red balls. So there are 4 red balls, so that is our part. And we are also kind of assuming here that, well, why don't we use the pink? So there are 4 of them out of, and then I need to know how many total, assuming the balls are all equal. So there are 7 orange, 8 green, and 4 red. So we're just going to count and add all of those together. I do a lot of mental math puzzles like Sudoku puzzles, but they involve sums. So I do a lot of single digit summations. I'm telling you guys this because I will do these kind of things in my head. That does not mean I expect you guys to. I would much rather you guys get proficient using a calculator consistently and correctly than stressing your brain out to remember how to add all the digits together. Like, your job is not to be able to do adding the digits in your head. Your job is to know that you're supposed to add them here. Let the machine do the machine's job. Be thankful you have it because your grandparents did not. So 7 and 8 is 15, and 4 more, 16, 17, 18, 19. So that is our total. 7 plus 8 plus 4 equals 19, the total. So, and this is where, like, the thing that comes to a lot of people's mind when you say fraction is part whole. The part we're talking about over the whole number. So that's what we see. The part we're talking about, the 4 red balls over the whole or the total. That's how we take the, like, how do I write an answer that is a fraction? How do I figure out where the numbers go? We say that part whole thing, but it's supposed to be the number of parts and the size the whole is split into, or the number of pieces the whole gets split into for the part whole. But I am babbling. And on YouTube, you can double time the talking. So now there are 365 days in a year. What fraction of this kind of year does August represent? Well, they gave us days, thank you. So we just have to figure out how many days August represents. And then we have the same units, which is important for writing a fraction. To have it be a proper fraction, you need the units to be the same kind of thing. So this isn't, I'm going to say it's 1 out of 12 months. Since they told us 365 days in a year, we're going to assume they want us to figure out how many days are in August and do that for the top number out of 365. So August, January, February, March, April, May, June, July, August. August is a 31. Yes, I have to count on my knuckles. It's the only way I remember which ones are which. It's a good trick if you don't know it. Just like how to use your knuckles to figure out the number of days in the month is definitely Googleable. Or ask me in office hours. I will be happy to explain. So there's our fraction. Now that might reduce, but 31 is what we call a prime number. So it's not going to get any smaller. The good news is on your scientific calculator, if you type 31 over 365 and you hit enter, the calculator will do one of a couple of things. One of which will be they'll give you the ugly decimal. There will be a button that says, no, I want the fraction. Or there's a setting where you say, give me fractions. I think on the Casios, there's like a SD button or an FD button. So it's like fraction to decimal, and it'll switch back and forth between the two. For some of them, if you input it as a fraction, then it'll output a fraction. And instead of using the division symbol, there'll be like a fraction button you can use. The thing is, though, the calculator will reduce the fraction for you. So we're going to talk about conceptually what that means, what we're doing, but it is totally legit to punch it on the calculator and see if it reduces that way. Use your tools. All right, our last one here in a statistics class containing 67 students. That's pretty big. 17 are math majors. That's really small. 31 are physics majors, and the remaining students are engineering majors. All right, what fraction of the class is made of engineering major students? All right, so 17 are math, 31 are physics, and the remaining students. So the rest, the leftover of the whole, are engineering students. So to figure out the number of engineering students, I'm going to take my total and subtract off the other stuff. So we're going to start with the total. Now you could, if you wanted, add 17 and 31 and then subtract that off the total. I noticed 67 and 17 will subtract nicely. But honestly, you guys just crunch it on your calculator. So that'll be 50, and then I'm going to take off the 31. I'd need 9 more to get to 40 and 10 more to get to 50. So it is 19, not 29 or 21. So there are 19 engineering majors out of a total of 67 students in the class. 19 is a prime number. I believe 67 is as well. I'm not as comfy with my larger primes, but that looked like a Z. So that's how we answer those kind of questions. So you should have a small set of those on your ALEKS homework. All right, properties of fractions. Yes, it's a big fancy thing and needed a big fancy voice. Not really. So suppose A and B represent non-zero numbers. That is because 0 within a fraction can do some weird things. So any fraction over 1, we just say is, sorry, any number over 1, we just say is that number. Because we're saying there are A copies, but each piece we're talking about represents one whole. Well, then you have A wholes. What? I did not do that on purpose, but it was funny. So in the example, we have 14 copies of pieces that are one whole unit size. So that's the same as just saying there's 14. We don't need to say 14 over 1. But this equality goes both ways. There are times where I do want to see that denominator if I'm trying to make everything into the same denominator. So putting it over 1 reminds me I have to do it to this too. So all of these equalities go both ways. Now, if I have 0 on top, remember our copies number of size of fractions. So there are 0 copies of a fraction of whatever size. Well, if there's 0 copies, it doesn't matter what size the fraction is, there's 0. So anything of that form is just 0, which means 0 can be divided by any number and you get 0. So you can put 0 over any denominator you want, except dun, 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 the dreaded dividing by 0. One of the first rules of math is we don't divide by 0. And we use the fancy word undefined. Now, if you type something like that on your calculator, it'll say or error or div by 0. It'll give you some sort of error message. Calculator does not like doing this and it gets mad. So that's when you know you have violated one of the two math rules. One is don't divide by 0. The other is don't try to square root negatives. I don't think we get to roots exactly in this course, but just, you guys have, I assume, seen radicals at some point, square roots at least. All right, now if I have a number over the same number, meaning if I have pieces split into a size, and then there are that many copies, that makes one whole. Doesn't matter what number a is, it can even be negatives. It's still going to equal 1, a positive 1 whole. Now 5 is just a property of the way negatives work. If I divide two negatives, it just becomes positive. And then 6 is if there's only a single negative, this is really more of a notational thing, but it is also if I arrive at a negative number over b, that is the same as the negative of that fraction, or that is the same as the negative just stuck onto the b at the bottom. So here, negative 5/12 is the same as negative 5 over 12, which is also the same as 5 over negative 12. So it is helpful sometimes to actually manipulate the negative that way in some weirder algebra problems. All right. And then just a quick putting it out there, simplify. So legit, you could type these on your calculator and it will simplify them for you. But most of these we should be able to do. I have 0 copies of negative 19ths. It's still 0. I have negative 43 copies of negative 43rds. Well, I know negative over negative is going to be positive. 43 parts out of size 43rds is 1 whole. So just 1. And then 8, I have 9 copies of things that are 1 whole size. So this is just the same as the number 9. But negative 3 over 0, I have negative 3 copies of size that are 0th size. That's not the same as 1 size. We just did 1 whole on 8. 0th size. Doesn't make sense. We don't know what that means. I'm just going to type it. There. And likewise, way over here on 11. Doesn't matter what the top number is. We don't divide by 0. That's the first rule of Math Club. And then here, the negative 17 over negative 2. Now, we haven't actually talked about reducing fractions, and you're going to notice the book is actually sticking with prime numbers here. That is deliberate, because if one of the numbers is prime, as long as it doesn't divide into the other one nicely, it's not going to reduce. So here, the simplified does not mean reduce. Later on, once we cover reducing, it will mean that. But for now, they're just make it look cleaner. So negative 17 over negative 2, those negatives cancel out. It is just 17 halves. All right, I'm going to cut this one here and then record the rest on a separate video. So catch you on the flip side.